So good morning students, welcome back. Today we'll discuss the second application of Biot's savart law. As you know, the previous lecture we did the first application. In first application we found the magnetic field at the center of current carrying coil, at the center of circular current carrying coil. Now today we'll discuss the second application in which we'll find the magnetic field. Magnetic field on x-axis due to current carrying circular coil. Today we'll find magnetic field on the axis. This will be the second application of Biot's savart law. So let's start with diagram. Look at students, the diagram. Consider a circular coil. Okay, that is a circular coil with radius, that is center with radius small a. Okay, this is the axis. Look at, this is the axis at which we have to find magnetic field. This coil having current I and that is flowing in clockwise direction. This is center of coil and A is the radius. We'll take partial length. We'll take two segments. One is upwards, another is downwards. We do two partial length DL. When current flows in this partial length, it generates magnetic field at certain point P. Look at students. When current flows in this partial length, we know whenever the current flows in partial length, it produces magnetic field according to Biot's savart law. So this is the direction of magnetic field dB. This is the point P. Look at since the direction of magnetic field is perpendicular, because in perpendicular direction magnetic field intensity will be more. So this will be the direction of magnetic field due to this partial length. Okay, now students, we can also find the direction by right hand thumb rule or palm rule. Okay, now students, when the current flows in this partial length, that generate magnetic field at point P. Okay, and this is the direction of that magnetic field perpendicular to the surface. Look at this upper portion will generate magnetic field in upward direction, and that produce in downward direction. Okay, magnetic field will generate perpendicular to the surface. Now students, this is the point P. Okay, let this angle is alpha. We can also take theta. This is 90 from O to P. That distance is x. Distance along x-axis, that is taken as x. Okay, and the distance from partial end to P point where we have to find magnetic field, that distance is taken as r. And suppose this is theta. Okay, now since this is x-axis, this is the x-axis where we have to find magnetic field, and distance along x-axis taken as x. Now we have to find magnetic field at P point. Now we'll make some change. That will be the construction part. Look at students. If this is alpha, this is 90, so this will be 90 minus alpha. Okay, and this is perpendicular. The direction of magnetic field is perpendicular. This is perpendicular. If this is 90 minus alpha, again this become alpha. Understood students? So now we don't require this, so we'll eliminate this. Similarly, this is alpha. This will be 90 minus alpha. Okay, and remaining this angle is again taken as alpha. So students, what we'll do, we'll find magnetic field at point P along x-axis due to current carrying circular coil. Okay, so first of all I'm going to apply Biot's savart law. What is Biot's savart law? dB equals to mu naught upon 4 pi IDL sin theta by r square. This is the Biot's savart law. Okay students, now what we'll do students, look at theta. For small distance, small segment, this is taken as straight line. So this is approx 90. We can say DL is perpendicular to A. DL partial length is perpendicular to radius. So theta should be 90. Okay, So here we'll make sin 90, and we know what is the value of sin 90. Sin 90 is taken 1. You can check this. So what will get, students? We'll get this step dv equals to mu naught upon 4 pi ideal by r square. Equation second. Understood? When current flows in partial length, it produces magnetic field at P point on x-axis. For finding that, what I did, I applied Biot's savart law. Mu naught upon 4 pi ideal sin theta by r square. This partial length is perpendicular to the radius, so theta is taken as 90, and sin 90 will be what? 1. So this will eliminate, and remaining term will mu naught upon 4 pi ideal by r square. You can take a screenshot. Okay, you can copy this. You can take a screenshot. Now remember that step only. Now students, look at this. We found dV, but one important concept is there. This magnetic field having two components. Along this is alpha, so this will be taken as horizontal component. So this dV, this partial magnetic field generated by this component, that having two component, dB cos alpha and around dB sin alpha. This is taken as horizontal component, that is taken as vertical component, because alpha lies with this line. So this is become horizontal component, that will be perpendicular. This that will be remains as vertical component. Similarly, this magnetic field generated by this component, when current flows in this segment, it produces magnetic field dB, and that having two component, horizontal as taken as dB cos alpha, okay, and vertical taken as dB sin alpha. So we will get an important conclusion that dB cos alpha are equal in magnitude and opposite direction. So these are cancelled each other, while dB sin alpha components are in same direction. When two components are in same direction, so which component will give you the resultant magnetic field, the net magnetic field? Yes, that will be dB sin alpha. So what will do, students? We'll write resultant magnetic field, that will be given by dB sin alpha. Why? Because cos alpha cancel each other, because these are equal and opposite, while dB sin alpha in same direction. So we'll get the resultant by dB sin alpha. Okay, students? Now students, what is the value of dB? Just we found the value of dB is mu naught upon 4 pi ideal by r square. That is the value of dB. I just put instead dB. These are the value of dB, and sin alpha remain as it is. So here we write sin alpha. Okay, students. Now here we require two components. We require the value of dl and we require the value of sin alpha. So I'm going to remove this component. Look at, students. What should be sin alpha? Here sin alpha is what? Perpendicular by hypotenuse. Okay. See, in this perpendicular is what? A is perpendicular. This is 90. So A is perpendicular and opposite to 90. R is hypotenuse. So we got the first component. We got the value of sin alpha. What is the value of sin alpha? A by R. So we'll put there. One more thing we required. Look, students. So just put here instead sin alpha. Look at, students. You can take a screenshot of that equation. Now here, look at. I'm going to make some change. Sin alpha is A by R. So instead sin alpha, I'm going to put here A by R. Understood, students? Okay. Now finally, what we'll do? Mu naught upon 4 pi I r square r a, r constant come outside from integration. We'll write b equals to mu naught upon 4 pi, okay, r square into r, that become r cube, mu naught upon 4 pi I 4 pi r square into r cube, and a also come outside, okay, so it become mu naught I a by r cube, and it remain only integration dl. What is meaning of integration dl? Total length of the coil, that is circumference, and we know if radius is there, what will be circumference? 2 pi a. So here integration dl means what? Total length of the coil, that is 2 pi a, total length of the coil. So look at friends, in that equation, in this equation I will make some change, one more change. B equals to mu naught IA upon 4 pi r cube, and instead integration dl will write 2 pi a. Now students, pi to pi cancel out, 2 to 4 cancel out. B equals to mu naught IA, pi to pi cancel out, okay, or 2 4 cancel out, and it remain 2 r cube. Okay, look it, you can take a screenshot of this. Again I'm going to write here. So what we got, again I'm going to repeat this step. Mu naught IA upon 2 r cube. This is the very first beginning form, magnetic field on x-axis at certain point P due to circular current carrying coil. Okay, this is for single turns. Okay, look at students, this is only the single turns. If we are having n number of turns, suppose small n is the number of turns, total number of turns. So what will be for n turns? Mu naught Ni A. Look students, at A into A, that become A square. Understood students? Mu naught IA, A into A become A square. So mu naught Ni A square upon 2 r cube. So look at friends, so we got the very first form. How much magnetic field generated on x-axis due to circular current carrying coil? For single turns, mu naught IA square upon 2 r cube, and for n number of turns, mu naught Ni A square upon 2 r cube. Now students, one more thing we'll find the value of r. For finding the value of r in this triangle, look at in this triangle, I'm going to apply Pythagoras theorem. A square plus x square equals to r square. R square equals to A square plus x square. A square plus x square equals to r square. When you remove square, there comes root. And what is the meaning of root? Root means power half. A square plus x square power half. Okay. So finally, I'm going to put the value of r here in this equation. So B equals to mu naught Ni A square upon 2. Yes, what is r? A square plus x square 3 into half, that become 3 by 2. So we got the final form students. How much magnetic field generate on x-axis due to current carrying circular coil? Current axis, mu naught Ni A square upon 2 A square plus x square power 3 by 2. Okay, you can see, and this is the very first beginning form. Mu naught IA square upon 2 r cube for 1 turns. For n turns, mu naught Ni A square upon 2 r cube, and this is the final form. So B equals to mu naught Ni A square upon 2 A square plus x square 3 by 2. Where n is the number of turns, I is the current of coil, A is the radius, mu naught is permeability, x is the distance along x-axis at which we found the magnetic field. So this is the final formula.